I'm Yolanda. You can also call me Yuan Tang. Either is okay. Thank you for having me here presenting our work, Superdiffusion of quantized vortices in a random vortex-tangle. This talk will include the following part. First is a brief introduction of the random tangle and the PTV technique used in helium-2, and also some other concepts that will be related in our later talk. The second part is our experimental results. I will talk about how we extract information of the quantum vortex lines and our study on their diffusion statistics. The third part is the simulation work we recently did to support our understandings. This is a phase diagram of the liquid helium-4 when the temperature is below the transition temperature, typically 2.17 K. Under the condition of atmosphere pressure, the liquid helium-4 will undergo a phase transition from its normal phase helium-1 to its superphase helium-2. Based on the two-fluid model, the helium-2 has two interpenetrating components. One is a normal fluid component, which has both non-zero viscosity and entropy. The other is a superfluid component, which has both zero viscosity and entropy. Today, we focus on the thermal counterflow in helium-2. For China filled with helium-2, as we apply some heat flux as a closed end, the normal fluid will flow away from the heater, and its velocity is proportional to this heat flux as given by this expression. Then the superfluid will flow towards the heater to compensate the fluid mass. As the heat flux is smaller than the critical value, both the fluid components are laminar. As the heat flux becomes larger, typically larger than 10 milliwatts per centimeter square, the superfluid component becomes turbulent, while the normal fluid is still laminar. Then we call this state as T1 state. As the heat flux increases further, typically larger than 100 milliwatt per centimeter square, both the fluid components becomes turbulent. Then we have a complex doubly turbulent system. This is what we call T2 state. Today, we will focus on the T1 state. In this state, the vortices are randomly oriented, and there is no coherent vortex bundle that can induce large-scale flow. That is, in this state, turbulence in the superfluid component will be induced by a random tangle of quantized vortices. In recent years, particle tracking velocimetry method have been adopted by many laboratories to study the real-time evolution of the helium-2 flow. For this method, typically, some particle will be introduced into the helium-2. Then a laser is used to illuminate those particles. Then illuminated particles is filmed by a high-speed camera for multiple consecutive frames. Using the computer algorithm, spatial locations of those particles will be identified. Then positions in multi-frames for individual particle will be tracked to link its trajectory. By tracking individual particles, their velocity can be calculated. Using this method, both Lagrangian and Euler analysis are possible. In the past, micron-sized solidified particles of hydrogen and its isotope deuterium, or D2 for short, have been successfully used in helium-2 as tracers. Those particles are usually formed by injecting room temperature gas mixture of hydrogen and helium, or D2 and helium, through an injection tube into the liquid helium. It has been proved by this paper that those particles are not only entrained by the viscous normal fluid, but can be trapped on the quantized vortices in the superfluid components. So in principle, by looking at those trapped particles, we can study the motion of quantum vortex lines. Now I'm going to report our PTV measurement in thermal counterflow. In our experiment, micron-sized solidified D2 particles are used. This is a size distribution of those particles, which is measured by the settling velocity in static liquid helium. The mean diameter of those particles is about 5 microns. This is a schematic of our experimental setup. An acrylic channel is immersed in the liquid helium bath. This channel has a square cross-section with the inner side length of 1.6 centimeters. A thin laser sheet passes through this channel to create a planar imaging area in the X-Z plane. Z and X-axis denote direction parallel and perpendicular to the counterflow direction. After the liquid helium bath is cooled to our target temperature, the room temperature gas mixture of D2 and helium will be injected through this tube just above the imaging area. Then this injection tube will be pulled out of the channel. After that, we turn on the heater, then wait for 5 to 10 seconds, take images. This is a typical video for 1.85 K and heat flux of 38 milliwatt per centimeter square. It is clear that some particles move straightly upward in the direction of the heat flux, while some others move irregularly and downward on average. We then extract the trajectories of those particles. Obviously, two types of trajectories are observed. The straight upward trajectories colored by the red, indicate particles moving with the normal fluid. And other erratic trajectories colored by the blue indicate particles trapped on the quantized vortices. We then categorize those particles moving with the normal fluid as group 2 particles, or G2 for short, and categorize those particles trapped on the quantized vortices as group 1 particles, or G1 for short. According to the experimental observations, at low heat flux, those two distinct groups of particles will appear. This is the vertical velocity distribution of those particles. It exhibits two nearly separate peaks. The G2 particles contribute to the peak with the higher mean value, while the velocity measurement of the G1 particles contribute to the peak with the lower mean value. In practice, to judge whether a particle belongs to the G1 or G2 group, we use the following algorithm. When the particle's instantaneous vertical velocity is smaller than this threshold, we consider this particle belong to the G1 group. When the particle's instantaneous vertical velocity is larger than this threshold, we consider this particle belong to the G2 group. The coefficients A1 and A2 here will be tuned to best distinguish those two groups of particles for each data set. This method enables us to extract the information of the particles moving with the vortex-tangle separately. In general, the trapped G1 particle may also slide along the vortex line due to the viscous drag effect from the normal fluid. However, according to the experimental observations, at low heat flux, the viscous drag force should be mild. This video shows several vortex lines taken by Fonda and his colleagues. It is found that the trapped particles appear to be nearly immobilized along the vortex line when the line does not move too fast. There is a physical mechanism behind this localization, which have been explained in this recent paper. Those observations suggest that the motion of the trapped particles can represent the true motion of the vortex line at low heat flux. Then we will, in the subsequent study, we will focus on the study on the G1 particles at low heat flux to study the quantized vortex line dynamics. Now we specifically focus on the apparent diffusion of the G1 particles in the horizontal direction, which is this direction is perpendicular to the counterflow direction. The purpose to choose this direction is because we want to keep the viscous drag effect from the normal fluid minimal. If we consider the mean square displacement for for the G1 particles, it will increases with time, which gives us t to the power of gamma. There are different diffusion regions. The diffusion is called subdiffusion if gamma is less than 1, normal diffusion if gamma equals 1, superdiffusion if gamma is greater than 1, and specifically, if gamma equals 2, the superdiffusion will be also called ballistic diffusion. Here we give the result of the mean square displacement of our G1 particle in the horizontal direction. This result is for the 1.7 K and the heat flux of 38 milliwatt per centimeter square. The diffusion time here starts from the moment when a particle first appears on the trajectory, and the angle brackets here denotes an example average of over at least 1,000 samples. The data are shown as the black circle. They appear to have two parallel regions. The first region was marked by the yellow. We then feed the data in this region. A parallel index of 1.63 is obtained as shown as the blue solid line, which indicates superdiffusion. We then feed the data at larger diffusion time. A parallel index of 1.1 is obtained as shown by the red dashed line, which indicates nearly normal diffusion. Then the intersection of these two lines give us a critical mean displacement separating those two parallel regions. We also conduct experiments for different temperatures and heat fluxes. Surprisingly, the data all shown two parallel regions. Then we collected the derived parallel index gamma 1 and gamma 2 in these two figures. The data, we always have a superdiffusion with parallel indexes between the 1.6 to 1.7 and a nearly normal diffusion with parallel index between 1.0 to 1.2. We also compared the critical mean displacement with the mean vortex line spacing. It is found that those critical mean displacement is comparable to the mean vortex line spacing. The natural question here is what causes the superdiffusion and why there is a transition to normal diffusion when the displacement is larger than the mean vortex line spacing. In general, for a particle undergoes completely random motion, their displacement distribution should be a Gaussian shape. This is essentially a normal diffusion. Well, it has been found in many physical and non-physical systems that when a particle exhibits long-distance hops, and those long-distance hops lead to a parallel tail of their displacement distribution with parallel index alpha here, with parallel index alpha smaller than 3, which means the tail is much flatter. Then those large distance hops will be called Levy flights. This Levy flights is considered to be the reason to lead the superdiffusion behavior. Interestingly, our G1 particle indeed have those large distance hops. Here we give the typical track of our G1 particle. This large distance hops is caused by the well-known vortex reconnection events. The details can be found in these papers. However, those large distance hops can only lead to parallel tail comparable or much steeper than the parallel index equals 3. Those observations suggest that large step events cannot explain our observed superdiffusion. Without invoking the Levy flight concept, another possible explanation for the superdiffusion is that the motion of our particle is not completely random. there may exist the velocity of the particle may exist temporal correlations. Then over time, their motion can have superdiffusion behavior. Here we give a mathematical formula that relates the mean square displacement and the corresponding temporal velocity correlations. If the temperature velocity correlation scales as t to the power minus beta, then the corresponding mean square displacement will scale as t to the power 2 minus beta. Then we examined the temporal velocity correlation of our data. This figure shows the result of 1.7 K and a heat flux of 38 milliwatt per centimeter square, which is the same condition as the figure for the mean square displacement shown previously. The data indeed show a power law scaling region shaded by this yellow area. We then feed the data in this area. A power law index of 0.4 is obtained, shown as the blue solid line. The corresponding mean square, the corresponding diffusion power law index is 1.6, which agree with our observed diffusion power law index, superdiffusion power law index 1.63. This observation suggests the following physical picture. For G1 particles moving with the vortices, when their displacement is smaller than mean vortex line spacing, there exists power law temporal velocity correlation that leads to the observed superdiffusion. When their displacement is larger than the mean vortex line spacing, vortex reconnections randomize the particle motion, which leads to normal diffusion at large time and length scales. To support our understanding, we adopted the vortex filament model with the 4-Biot-Savart law to simulate the vortex dynamics in thermal counterflow. We choose a cubic computational box with a set length of 1 millimeter. The spatial resolution is 0.01 millimeter. The other parameters are listed here. And every discrete point along the line will be assigned with a unique index, and their positions will be all tracked. We then used the above method to conduct a simulation here. The vortices are evolved from 6 rings. This is a typical video for 1.6 K and the counterflow velocity of 5.5 millimeter per second. We calculated the time evolution of the vortex line density and counterflow direction anisotropy of the vortex tangle based on the data shown in this video. They both evolved to steady state after about 9.4 seconds of the simulation time. We will calculate our statistical analysis in the steady state. We also conducted the simulations for different counterflow velocities. Their steady state mean vortex line density agree with the published numerical and experimental results. These results validate our model. By tracking every point along the lines, every discrete point along the lines, we calculate the mean square displacement in the direction perpendicular to the counterflow direction, which defined at the lower right. We plot the data in this figure. The data in these two directions collapse together. This green line indicates the root of the mean square displacement equals the vortex line spacing. This line separates the data into different power law regions. We then feed the data shaded by red. A power law indexes of 1.62 and 1.61 are obtained, shown as the same bold solid line and blue thinner solid line, which indicates superdiffusion. Then a guiding line indicating the normal diffusion agrees agrees the data shaded by yellow in some extent, which indicates the data at the larger diffusion time is a nearly normal diffusion. Then at enough small diffusion times, the velocities of the particles will be fully correlated. Then the data will start to show a ballistic scaling. We are also conducting other simulations for other counterflow velocities and temperatures, and more results will come in the future. We then calculated the superdiffusion indexes from the experimental and simulation results in this figure. Those results agree well with each other and looks independently of the temperatures and heat fluxes. This indicates that the superdiffusion is likely a generic property of the evolving random tangle. At the meantime, Satoshi and his colleagues are also conducting simulation work, including aiding particles in thermal counterflow. Their preliminary results are in good agreement with our findings. We are going to coordinate publications. Thank you. These are all my presentations.
Thanks very much for a really interesting talk. Again, any questions, please raise hands or just pop something in the chat and I can ask on your behalf. So John, you've got your hand.
Yeah, thank you for the talk. I just have a quick question about your particles. So they're, you said like 4.6 microns, right?
Yeah.
But they're trapping on the vortex core, which is much smaller. Do these particles themselves have then an effect on the vortices and on the turbulence itself, or do you really think they're completely inert in this way? They seem too big for me.
Yeah, for this work, we assume that at low heat flux, the particles has like minor effect on the motion of the vortex lines.
Do we believe that's really true? I mean, this is just a kind of a general question. I'm.
And so to support this, we conduct the numerical simulations, and the simulation result agrees with the experimental result. So, which indicates that the effect of the particle on the quantized vortices, the motion of quantized vortices, is minor. Yeah.
Okay, thank you.
Thank you.
So next up in the order, I think it's Patrick. I think you may also be muted, Patrick.
Can you hear me now?
Yes.
Yeah, that's good.
Perfect. It's my mic that didn't work. So, okay. So thanks for the talk. I just would like to ask a question about this fact that you can actually split the statistics into these groups, G1 and G2. So do you observe some different behavior for this group? I believe it's called G2, where the particles follow the normal fluid.
Yeah. Oh. What do you mean the different behavior? You mean the diffusion statistics?
Regarding the superdiffusion.
Oh, actually, we didn't analyze those group of particles. We just focus on the G1 particles.
Mm-hmm.
Yes.
Okay, I mean, interesting point of interesting idea to try. Yeah.
Thank you.
Philippe.
Thank you. Hello. Thank you for the nice talk and interesting work. Counterflows are not isotropic. The tangle doesn't have the same statistics perpendicular to the mean direction and in the heat flux direction. So now you are looking, if I understand properly, at the statistics, super diffusive properties in a ZX plane. So intuitively, I would expect the diffusion properties in the X direction and Z direction to differ. So how do you take this into account in the interpretation?
Yeah, we actually do some very rough study on the direction like of the counterflow. In the counterflow direction, the diffusion like index is indeed different from the direction perpendicular to the counterflow. But we are still thinking how to explain this. We are still studying on how to explain this and why the diffusion index is different and how does it come?
Yeah. Can I comment, Philip?
Sure.
This is actually a very good question. We are quite interested in the possible difference in the counterflow direction and perpendicular direction. So actually, we did some research. We started the diffusion in the heat flux direction and in the moving frame at the mean velocity of the vortex-tangle. It turns out that the diffusion index is slightly different. This result has not been reported. We're still working on it.
Okay, thank you.
Yeah.
So we've got time for one more quick question.
Well, maybe I have another one if nobody has any.
The floor is yours, Philippe.
Yeah, thank you. Well, maybe I misunderstood the talk. Sorry for my English. So you explained the superdiffusion behavior by correlation of the So
velocity, yeah.
I can imagine the several mechanisms for this correlation. First, this because of I don't know a large scale circulation, the entrance effect, lateral thermal counterflow due to the thermal windows, settling time, a non-flat profile for the velocity, non-flat profile for the normal fluid. So have you been able to identify where does this correlation come from? Is it intrinsic or is it properties of the experimental setup? You see what I mean?
Yeah, this is a good suggestion. Actually, we haven't go this further to to study what's this correlation comes from. Yeah, we can. Yeah, this is a good suggestion. We can.
Well, sorry. Let me comment on this again. I think this is generic because Yolanda did the numerical simulation and also Satoshi and the Makoto's group also did some simulation. They showed that even in the numerical simulation, such superdiffusion can still be observed. So it's independent of the facility, for sure.
Okay.
Okay, well that brings us to 5. So unless anyone's got anything burning they want to ask, let's end there. So I hope you all please join me in thanking both the speakers for a pair of interesting talks today. Managed to get my clappy hand going. So the next talk in the series is in 2 weeks' time, and if you join us, Alina Blinova from Massachusetts Amherst, we're talking about the controlled creation and splitting of singly quantized vortices in a polar phase BEC, and that's at 4 UK time. Okay, well, thanks everyone for attending, and hope to see you in a fortnight's time.
Thank you, everyone. Bye.
Thank you.